Let us now understand how we can explain this observation that when parallel beam of light passes through a gap in a wall, okay, it diverges. Now, a parallel beam of light, as we have just discussed, has a planar wavefront. Right? On screen, okay, which is a two-dimensional surface, the wavefronts look like lines. So this is one wavefront. All points here will be in phase with each other. You imagine wavelets being emitted by each of these sources. Okay, as the light is traveling forward, okay, at a particular moment, let's say this set of particles got disturbed. Then what this set of particles will do, it will disturb the layer next to it. So you have to imagine wavelets being emitted by each of these particles. How do you do that? You just draw small circles around them. I'll just draw two or three. And you take a common tangential surface to these wavelets. The common tangential surface you get will be like on screen, it looks like a straight line. In 3D, it will be a plane. Okay. So this wavefront, which looks like a line, in some time moves forward like this. Okay, and so on. That set of particles now disturbs the next set. That is how energy basically propagates. Okay, and here itself you can see the explanation also to this phenomenon. This first wavelet that we have drawn and this last one. Okay, if you observe carefully, you can see that they are also sending energy or emitting energy in these directions, right? The disturbance created by those particles will spread in all directions. And disturbance created by other particles also, it spreads in all directions. Most of the disturbance or most of the energy continues to propagate forward this way. But there is some energy diverging also. So a parallel beam of light actually doesn't stay parallel. Okay, it will automatically start diverging. But most of the energy stays on that parallel beam. Okay. So when this parallel beam strikes the wall also, and you consider the gap in the wall, you can see that the wavefront is present here. Okay. Imagine every point on the wavefront as a source of waves and draw wavelets. You'll get infinite number of wavelets like this. Okay, we are just visualizing a few. So that wavefront continues to move forward. Okay, it will still be a planar wavefront only. Most of the energy travels along the main parallel beam. Okay, but some energy gets diverged like this also. So Huygens, using wave theory, was able to explain why this happens with light. Because he observed that happening with water and sound waves. The same explanation he uh, extended it to light. Okay, but as I said, those days, okay, or initially, it was believed that light is a collection of particles. They didn't know that light had wave nature. But this behavior of light could only be explained if you consider it as a wave, consider light as a wave. Okay, fine. So then they got this doubt that maybe light has wave nature because it is behaving like waves. Fine. And they already knew these phenomena of reflection and refraction of light. So there had to be some way, okay, if they believed that light is a wave, there had to be a way to uh, explain reflection and refraction of light also by considering it as a wave, okay, in terms of Huygens wave theory. So let's see how they did that. Reflection will be quite easy. You understand how refraction was explained using wave theory, then you can easily explain reflection on your own. Okay, so let's look at how Snell's law is derived from Huygens wave theory. Now, suppose there's an interface separating two media. Let's say there's one medium above in which the light travels faster. Okay, and there's another medium below in which light travels slower. Okay, based on the medium, the speed of light, not just light, based on medium, the speed of waves will vary. Okay, now usually what we observe in refraction is when light is incident on the interface between two media, at the point of incidence, it bends. Okay, depending on the speed of light in the medium, it could bend towards the normal or away from the normal. Okay, fine. So basically, we have to explain the bending of light in terms of Huygens wave theory. Okay, let's see how that was done. So what you need to understand is in ray optics, we call this as a ray of light. Okay, we draw one line and we call it as a ray of light. Actually, a ray of light is a beam of parallel waves. You have to look at it like that. Okay, a single ray consists a large number of waves, light waves, traveling parallel to each other. That is what we call as a ray. Now, we just discussed that a parallel beam cannot stay parallel. Okay, it has to diverge. But most of the energy continues traveling in the parallel direction, like in the direction of the parallel beam. So that is what we effectively call as a ray of light. Okay, so you have to look at this as a collection of waves. So let us look at it that way. Assume this is the interface between the two media. So you have to now imagine a beam of light being incident like this. A parallel beam, that too. A parallel beam, has a planar wavefront. Okay. I'll indicate the wavefront in black. And can one of you quickly tell me what is the angle between direction of propagation of wave and its wavefront? Angle between direction of propagation of wave and wavefront is 90 degrees. Okay. So if ray is going to strike the ray is about to strike the surface at an angle like this, you can automatically draw the wavefront. Okay. Right. So let's imagine the ray as a thick beam like this, thick parallel beam of light. Just for us to be able to visualize, we have to imagine it to be thick like this. So this is one wave. This is one wave. In between, there will be infinite other waves. So a ray of light, as I said, is a collection of parallel waves. Okay. Just a moment. I'll take some 4 or 5 waves. They all share this common wavefront. Okay, imagine it like this. Fine. So this whole set of waves is what we call as one ray, the incident ray. Okay. You can visualize the angle of incidence as well. Let's draw a normal here. this line is a normal drawn at the point of incidence, okay, of the first wave, I can say. The entire ray, if you consider, each wave of the ray can have a different point of incidence. Fine. In like when we look at it, what do you say? When we look at it in the macroscopic scale, it looks like a single line, okay, single beam of a single ray of light, but it's actually a collection. That collection of waves can strike the surface at different points. Okay, in fact, they do strike the surface at different points. Now here, the incident light is just touching the interface between the two media. Okay, this is the interface. Fine. Above the interface is the faster medium. Below the interface is the slower medium. Okay, I still didn't talk about refractive index. Okay, we are just looking at what happens, or we are just trying to explain what happens when light enters from a fast moving medium to a slow moving medium. Okay, now how is the ray propagating forward? The ray propagates like this. Every point on the wavefront will behave as a source of waves. You imagine wavelets around them. Like this. We'll go a little slow only because this is important. It's important to visualize how wave propagates if you want to answer questions properly. So basically, you just have to draw circles with centers at points on the wavefront. Okay. So at a particular instant, when the wavefront is here, each point on the wavefront would have behaved as a source of waves, source of disturbance. So imagine the disturbance propagating outward, and the wave effectively, not the wavefront effectively moves forward like this to this position. The same thing happens here. Okay, you will again have to visualize each point of the wavefront creating a disturbance, and so on. You know the picture. Okay, so let's say the wavefront has just arrived at the interface. Now, everywhere above the interface, the medium is uniform. So all these wavelets, these circles that we have drawn, they are called wavelets. All these wavelets in a certain amount of time would have expanded to the same radius. Okay, all these wavelets will have the same radius. What radius is that? Speed of light in the first medium multiplied with the time after which you want the position of the wavefront. Okay, that's the radius by which they would have expanded. Okay, but let's say the ray, which is basically a collection of waves, has just arrived at the interface. Then you imagine what happens with the first particle. Okay, let's name the number the particles. 1, 2, 3, 4, 5. I'm considering 5 points on the wavefront. Okay, actually there are infinite points on the wavefront. I'm considering 5 of them. Each one of them will start disturbing the particles around it. Now you see the first particle. The first particle has first point of the wavefront, not particle. Okay, this could be happening in vacuum also. The first point of the wavefront, it has one medium on one side, another medium on the other side. Okay, that point will disturb surrounding points, but the disturbance travels at different rates in different media. So basically what happens if you allow the same time delta t, in the first medium, the disturbance will propagate like this. Just a moment, I need to adjust this. If you allow the same time delta t, in the first medium, which is the upper medium, the disturbance would propagate to a distance v1 delta t. Like this. Its surrounding particles in the upper medium, it will disturb this way. Okay, and the disturbance will propagate to the distance v1 delta t, as I said. But in the second medium, the disturbance travels slowly. Okay. As a result, what will happen? Let's say the speed in the second medium is v2. Then as a result, the disturbance will only propagate a short distance in the second medium in the same amount of time. So in the lower medium, this is what you will observe. Okay, you can take it much smaller also just to visualize better. Just a moment. Okay, let's take it like this. It is disturbing the particles around it, but the disturbance travels slower in the second medium. So this is what happens to the wave front. Okay, not yet. We have not drawn the wave front, but this is the wavelet created by the first point of the wave front. The other points of the wave front also will be creating disturbances. And you imagine the other points of the wavefront creating disturbances. The second point, if it creates a disturbance, now second point we have taken comfortably above the interface. So even if it creates a disturbance, the disturbance will be entirely in the first medium itself. Okay. And for the second point itself, if it's in the first medium, then for the remaining points, the disturbance will anyway be completely in the first medium. So those will be proper circles. Okay. The set of particles that they disturb in a certain amount of time, they will be proper circles. Okay. So these circles all have radius v1 delta t, but this semicircle that you see here, the disturbance created in the second medium has a radius v2 delta t now. Because in the second medium, the disturbance propagates with a speed v2 itself. You can't do anything about it. Okay. Now, how do we draw wavefront? The wavefront is nothing but a common tangent drawn to all these wavelets. So imagine the light propagating forward now. Means it is entering into the second medium. Till now it was completely in the first medium. Now it is entering into the second medium. How do you draw the wavefront? Draw a common tangent to all these wavelets. If we do that, we get something like this. The wavefront effectively bends, okay, when it enters from one medium to another medium. I think it'll be better if I draw it as a thick line. You'll be able to visualize better. Okay, this is what happens to the wavefront. It's no longer a straight line in the plane of your screen, or in three dimensionals. If you 3 dimensions, if you imagine, it's no longer a perfectly flat surface. Okay, here it's flat at one angle. Here also it's flat, but at another angle. So the entire surface, if you see, it's a bent surface now. Okay. Now imagine the disturbance propagating forward. The wavefront has bent. Still, each particle on this wavefront now acts as a source of waves. So you consider them as new sources. I'll mark them in orange itself. So this is the first source now. This is the second source. Second source you imagine has just arrived at the interface. Third source is here. Fourth is here. Fifth is here. Okay. Now the first source of waves is entirely in the second medium. Okay, it has entered inside. So if you imagine wavelets from that first source, they will travel slowly in all directions now. So this is the wavelet produced by the first source. The second source has just arrived at the interface. Then what will happen with the second source is what happened with the first source earlier. In the upper medium, it will be able to disturb particles up to a greater distance because the speed is more. But in the lower medium, okay, the second medium, it will only be able to disturb particles up to a shorter distance because the speed there is v2. So radius will be v2 delta t. This is what happens. Then what about the remaining sources? The remaining sources we have considered them comfortably above the interface. So the disturbance that they create propagates uniformly in all directions because they have the same medium all around them. Hope this picture is clear to all of you. If you have any doubts, you can ask. Hope you can visualize how the wave is traveling. So now at this moment, if you draw the wave front, okay, at this instant, if you draw the wave front, you just have to draw a common tangential surface to the wavelet. So it goes like this. This is what happens to the wavefront, bent. Okay, so you continue visualizing this. We don't have to spend so much time on this. I mean, we don't have to draw the wavelets and all again. You get the picture. So you continue doing this. After another small duration of time, the wavefront will be like this. Some more time later, a little while later, be like this. And finally, the wavefront completely enters into the second medium at this angle. Okay, so before or when the ray is just incident on the interface, the angle made by the wavefront, I'm not talking about angle made by the ray. Okay, the wavefront was at this angle. Okay, was along this line. Finally, when the light enters into the second medium, the wavefront is along this line. And you know, wave direction has to be perpendicular to the wavefront direction. So light that enters into the second medium effectively travels perpendicular to these wavefronts. So it effectively travels like this. So let me complete this picture, just a moment. Right. So this parallel beam, which was traveling like this, every wave of that parallel beam now bends. Okay, now changes its direction. I'll tell you why it is very important to understand this derivation. It just depends on what they want to ask you. Okay. So finally, okay, these don't look parallel. Just a moment, let me. Okay. So finally, when light enters into the second medium, it travels like this. Now, this bundle of waves also, which is traveling in the second medium, appears like a ray to us. It also appears like a single ray only. So the ray of light which entered this way, the ray of light which entered at this angle now effectively propagates in the second medium at this angle. Okay, this is what we call refraction of light. Okay. Now we need to prove or derive Snell's law. Can one of you tell me the equation of Snell's law? Equation for Snell's law.
Mu2 sin I is equal to mu1 sin R. No,
Wrong.
mu1 sin I is equal to mu2 sin R.
Mu1 sin I is equal to mu2 sin R. Okay. Fine. Let's just consider this part of the diagram. Or okay, I think this picture itself is better. So mu1 sin I is equal to mu2 sin R, and fine, mu1 refractive index is C divided by V1, speed of light in vacuum divided by V1, and mu2 is basically C divided by V2. Okay, now as we know, this is what is refractive index. So the relation that we are trying to derive, just a moment, the relation that we are trying to derive is mu1 sin I is equal to mu2 sin R. Now mu1 is C by V1, mu2 is C by V2. C's cancel. So basically what you want to prove is sin I by V1, okay, that is the speed of light in the first medium, is equal to sin R by V2, speed of light in the second medium. Okay. If you see, now you know that angle of incidence is nothing but the angle between incident ray and the normal. So this angle here is the angle of incidence. And angle of refraction is the angle between refracted ray and the normal. So this is the angle of refraction. You need a relation between sin I and sin R. Let us zoom into that part of the diagram. Okay. You can clearly observe two triangles here. Okay, I'll highlight them, one in yellow and one in another color. So in the first medium, you can see there's a right angle triangle like this. Okay. Now the two triangles have a common side. That common side will take in black. So this is one triangle, and the other one formed in the second medium is this. Okay, these two are right angle triangles. Okay, because the right angle forms between the wave and the wavefront. Okay, right. What are the angles here? Angle of incidence we have to visualize. This angle is angle of incidence. Okay, if that angle is I, then this angle here will be 90° minus I. Okay, because this is wavefront, the angle is 90 degrees. So if one part is I, the other part has to be 90 minus I. Then the part inside will be I again. Which is that part? This one. Just a moment. This angle will again be I. Okay. Fine. My choice of colors is not that good. Never mind. And here, this is angle of refraction. If this is angle of refraction, then the angle inside here, this one, will be 90 minus R. That means the angle on the opposite side, okay, angle on the other side will be R. This angle is R. Okay. Let's say to enter from the first medium completely into the second medium, light takes a time of delta t. Okay. Now, in the first medium, light travels faster. Second medium, it travels slower. So, in the time delta t, in the time interval delta t, this distance that light travels in the first medium is V1 delta t. Okay. And this distance that light travels in the second medium in the same interval is V2 delta t. Okay. Or delta t dash also you can take. Any amount of time you consider, not an issue. So like this is a set of waves, right? From the moment the first wave changes its direction, to the moment the last wave changes its direction, the interval I'm taking is delta t dash. Okay, so in that time delta t dash, in the first medium, the waves would travel v1 delta t dash. In the second medium, they would travel v2 delta t dash. Okay, so in this triangle, this side is v1 delta t dash, and this side is v2 delta t dash. That's the amount of time taken for the light to completely enter into the second medium. Okay, and these two triangles have a common side. Now in the upper triangle, upper right angle triangle, you can see that sine is nothing but opposite by adjacent. Opposite is v1 delta t divided by that adjacent side, you can call it as AB if you want. The common side to the two triangles, you can call it as AB, or you can call it distance D also, whatever it is. That becomes the, wait, opposite by hypotenuse, sorry, not adjacent. What am I saying? The hypotenuse of the right angle triangle, you can call it as AB. Fine. In the triangle below that line, in the second medium, sine R, opposite side is V2 delta T divided by hypotenuse. Hypotenuse is AB again, common. Okay, that's all. You divide these two. You get sine I divided by sine R is equal to V1 by V2. So you can say sine I divided by V1 is equal to sine R divided by V2, and multiply C on both sides. Nothing wrong in that. You can multiply a non-zero number. And this is how you get Snell's law. Mu1 sine I is equal to mu2 sine R. Is the derivation clear to all of you? You have to visualize every particle of the wavefront producing wavelets. Then you can explain why light bends. It's actually the wavefront changing its direction. If the wavefront changes its direction, light changes its direction. Okay, the ray of light. So this complete beam of parallel waves is what we call as a single ray usually in geometrical optics. Okay, but you have to think of the ray as a set of waves like this. Then you can explain how all this happens. Okay. Now, why are we stressing so much on the derivation? Because they can ask you questions. It's an important concept. This basically explains the behavior of light, okay, in terms of wave nature. Okay, one question you can be asked. Try this, all of you. Let's say refractive indices are given to you. I want the answer in terms of mu1, mu2, I and R. Okay, so mu1, mu2, I, R, they are all given to you. What I want you to find out is thickness of the ray. In the first medium, let's say the thickness of the ray or the width of the ray, I can say, assume it is T1. Okay, in the second medium, it obviously looks wider. Okay, it clearly looks wider. Let's call this thickness as T2. Derive a relation between T1 and T2 in terms of mu1, mu2, I and R also. Okay, solve this problem, all of you. Derive a relation between T1 and T2 in terms of mu1, mu2, I and R. Solve this carefully. I'll give you all 2 minutes. Fine. So I got one answer as tan I divided by tan R is equal to V1 T2 by V2 T1. We'll see. You can convert it to mu1, mu2 terms also, not a big deal. Okay. Rishi, Isha, you also try and send your answers quickly. I'll give you 1 more minute. Right. See, T1 is one side of this upper triangle. This side is T1. T2 is one side of the lower triangle. Simple. You just have to relate those two sides. Rishi, how are you trying to do this? The two triangles have a common side. You can see the angle of incidence, angle of refraction also in the triangles. Okay, fine. In the upper triangle, T1 is the adjacent side to the angle of incidence I, and AB is the hypotenuse. Which trigonometric ratio relates adjacent and hypotenuse? Cos. So you can write cos I is equal to T divided by AB. Cos I adjacent is T1 divided by hypotenuse is AB. So cos I is equal to T by AB. T1 divided by AB. In the other triangle, for the angle of refraction R, T2 is the adjacent side, AB is the hypotenuse. That's all. So cos R becomes T2 divided by AB. That's it. This is the relation between them. Divide them. Cos I divided by cos R is equal to T1 by T2. Okay, you don't have to know I, R, mu1 and mu2. I and R are sufficient. Is this clear to all of you? Simple trigonometry is what you are expected to use. Okay, look at these triangles once again. Ask if you have any doubts. Pradyun, what exactly are you trying to divide to get in terms of tan? Okay, you wrote tan I is V1 delta T divided by T1. And you wrote tan R is equal to V2 delta T divided by T2. And you wanted to divide them. Okay, that also can be done. Okay, let's do it that. Let's look at it that way also. Tan I is opposite side V1 delta T divided by adjacent side T1. Okay. That approach also has its own merits. Tan I is V1 delta T dash divided by the width T1. And tan R will be V2 delta T dash divided by the width T2. Divide them. So you get tan I divided by tan R is equal to delta T dash is common, gets cancelled. V1 thickness T2 divided by V2 thickness T1. Okay. And here you can fine. So tan I divided by tan R becomes, see, V1 by V2 is nothing but mu2 by mu1. Okay, mu is inversely proportional to speed, no? So this becomes mu2 by mu1 into T2 divided by T1. This is also a relation, but tan I is nothing but sin I divided by cos I. Okay, so let's take this as sin I divided by cos I, and tan R is sin R divided by cos R. So effectively what will happen? Send the mu1 this side, it becomes mu1 sin I, and send sin R that side, mu2 sin R, they'll get cancelled. Okay, mu1 sin I, mu2 sin R, they'll get cancelled. And finally, you'll again be left with cos R divided by cos I is equal to T2 by T1, or cos I by cos R is equal to T1 by T2. I think that is what we got before also. You can express it in terms of tan, no problem. But final relation you get will be the same. Rishi and Isha, did you understand?
Yes, sir.
Okay, you seem to have some doubts, but try to do this once again. If you still have doubts, you can ask anytime, no problem. Okay. Next, just a moment, I'll paste one question. Right. So a parallel beam of light strikes a piece of transparent glass having cross section as shown in the figure. The correct shape of emergent wavefront will be. Okay. So finally, when light comes out of this glass slab, what is the shape of the wavefront? What is incident is a parallel beam of light. And we know parallel beam has a planar wavefront. Okay. So think carefully and try to solve. I'll give you all 3 minutes. Okay. Any answers, anyone? Or any ideas? Okay, listen. One face of the glass slab is flat. Okay. And the incident ray is perpendicular to that face. Okay. So basically, the light undergoes normal incidence here. When light undergoes normal incidence, we know it will pass without deviation. In terms of wavefronts also you can explain. Consider a wavefront here. Parallel beam has planar wavefront on the plane of your screen. It looks like a line. Okay. And that wavefront, assume it is just incident on the surface of the glass slab. So when the wavefront just reaches the surface, you imagine it to be, okay, imagine it to be here. Each point on the wavefront behaves as a source now. Okay. So when light just enters into the glass slab, so basically what we are discussing here is why light does not bend when it undergoes normal incidence. Okay. First thing that we have to see, that we'll have to discuss is that. So when the wavefront is just incident at that surface, now it is entering from air into glass. Okay. In the glass, the speed of light will be less. So just a moment, let's consider it like this. If you look at the wavelets, every particle on the wavefront will disturb the surrounding particles. Okay. So basically some particles in the, not particles, I should say points. Some points in the glass will get disturbed and some points in air will get disturbed. Okay, 1 second. Fine. We know light travels faster in air. So the disturbance in air travels a greater distance, whereas the disturbance inside the glass travels a shorter distance like this. Okay. So these are wavelets emerging from this source. Similarly, from the other sources also, you can imagine wavelets. 1 second. Okay, never mind. Okay, on the left side, uh, where there is air present, the wavelet will expand to a greater distance. Right side, inside glass, it will expand to a shorter distance. Okay, but still, if you draw a common tangent to all these wavelets that are now in glass, that common tangent will still be a flat surface. Okay, so basically what happens is the light continues to propagate in the original direction. So this is an explanation of why light does not bend when it undergoes normal incidence. Okay, so it will enter into the glass slab in the same manner as it was traveling in air. That's fine. But as it propagates further, the wave front, assume it just arrives at the air glass interface on the other side. The other side, air glass interface, is not flat. So let's say the wavefront has just arrived here. Then what happens is what you need to uh, like visualize to be able to answer this question. Now see that air glass interface on the right side, it has three semicircular parts. You can imagine it like that. Okay. Now whenever you see questions like this, no, suppose in a final exam you see a question like this, what you have to do is you have to break it down into smaller parts. Okay. Visualize what happens if there is only one semicircle. Then you can answer what happens when there are three semicircles. Okay. So let's consider that now. So suppose there is a semicircular boundary separating two media. Okay. To the left of this semicircle is glass, and to the right of this semicircle is air. Okay. I'll take light in orange color. Let's say this is the wave front that has just arrived at this curved interface. Okay, we don't have to take it that big also. The wavefront has just arrived at this curved interface, and I'll mark a few points on this wavefront. Each point behaves as a source of waves, secondary waves. Okay, those are the points from which we are going to draw wavelets. So consider one point here, one here, and one here. You can call them sources 1, 2, and 3. Okay, so how was light traveling? Till it uh, struck this interface, light was traveling like this to the right. It was a parallel beam. Okay, now the wavefront has just arrived at the interface. Imagine them producing wavelets. In glass, the wavelets or the disturbance travels slower. In air, it travels faster. Obviously, that point you have to keep in mind to answer this. Okay. So in air, it travels faster. In glass, it travels slower. For faster, we'll use a bigger circle. Slower, we'll have to use a smaller circle. Right. So first source, it is completely in glass. Okay. So if it produces a wavelet also, it will be a perfect circle, and that circle will be entirely in glass itself. Okay. In glass, the speed is slower, so the circle will be small. Same happens with the last source also, third one. Okay. But the middle one, second, it's at the interface. On one side, left side, disturbance travels slower. Right side, the disturbance travels faster. So left side, the wavelet will propagate only to a small distance. It will be like this. Okay. Right side, it will propagate to a greater distance. It will be like this. Okay, roughly speaking. So now look at what happens to the wavefront effectively. Till some distance, it will be flat. I mean, it will be parallel to the original wavefront. Right? But inside, it would have curved like this. Okay, I just drew one wavelet inside. Other wavelets also, if you consider, you will be able to, I mean, you can understand why it curves like that. Now imagine this light continuing to move forward. Okay, again, these three sources, this one, this one, this one. In fact, you consider other sources also. This one maybe. Okay, imagine them producing wavelets. A small duration later, okay, a small amount of time later, the wavefront will take this shape. The flat part will be much smaller now, and the curved part will be much bigger. It will be kind of like this. And once it completely enters into air, okay, from glass, once it completely comes out into air, it is going to emerge this way. That's all. Now you can answer the question. When the surface is curved to the left, convex to the left, the wavefront is convex to the right as it goes from glass to air. So these wavefronts that we have drawn here, you can now predict how they are going to emerge out of the glass-air interface. Where it is convex to the left, the wavefront emerges convex to the right. And where it is convex to the right, the wavefront would emerge convex to the left. Okay. So finally, when light completely comes out of this slab, it the wavefront will be shaped like this. Okay. First option is the correct answer. Is this clear to all of you? You have to imagine waves propagating, or you have to imagine wavelets. And based on that, you have to tell how the wave propagates. Then only you'll be able to answer. Okay, this was JEE advanced question. I don't remember which year. Okay, 2020. Fine. And recently they had given one more question also. Try to answer that. Okay, you can like recollect what we discussed here. I'll just paste the other question. Okay, it's this thick slab is made of material which allows light to pass through it. But you see there is a gradient. So basically what is happening is the refractive index of this slab close to the upper surface is N1 and close to the lower surface is N2, and N2 is greater than N1. Okay. So basically as you go down along the slab, the refractive index of the material increases. Okay. So you can think of this slab as a collection of sheets, each sheet made of a different material, okay, whose refractive index increases as you go down. Okay. Imagine a beam, a parallel beam of light incident on this, what do you call, slab. So parallel beam of light, just as in the previous case, you can imagine. Okay. Draw the wavefront after it enters into the medium. Okay, after it enters into the slab. Draw the wavefront just after light enters completely into the slab. Okay. Any answer? Can one of you describe the shape of the wavefront after it enters into the slab? Okay, Rishi, unmute, we'll discuss.
Yes, sir.
Huh. The first thing you have to do is imagine sources of disturbance at points on the wavefront. They create disturbance, you have to draw the wavelets. Okay. Now left side, for all of them, the medium is the same. It's air. Okay. So the wavelet drawn in air, okay, the wavelet drawn on the left will be same for all of them. Okay, I'm showing wavelets in orange. And that doesn't matter also. Okay, that back wave doesn't matter anyway. So it will be the same for all of them. I'm just showing for two of them. You don't have to draw for all. Okay. Rishi, tell me, the disturbance that they create in the slab, will it propagate to the same distance from every source?
Yes, sir.
How are you able to say that? In a certain
So
amount
once
of
again,
time.
can you repeat
Okay,
your
I'll repeat
question
my
once?
question. In a certain amount of time, in a short amount of time, dt, okay, from this instant to the next instant, all these sources will emit a wavelet or will create a disturbance in the slab. What I'm asking is, the disturbance created by each of these sources, will it travel the same distance inside the slab? Will the disturbances travel the same distance inside the slab in a given amount of time?
Yes, sir, they should.
Why should they?
Sir, because it's being emitted from the same source, right? And
So,
when all of
no. There are five different sources here. Okay, each point on the, in fact, there are infinite different sources. Each point on the wavefront behaves as a source. We have considered five sources. Okay, they'll disturb the particles around them. Okay, so the first source disturbs particles next to it. Second source disturbs. Third disturbs. Fourth disturbs. Fifth disturbs. The disturbance, will it travel with the same speed, is what I'm asking. Pradyun, we'll talk about interference in the next class. For now, let us not get into that. We just want to find out by what distance or how the wavefront bends. Okay, that is what we want for now. Interference can take place. Possibility is there. Okay, we'll see. Okay. See, how far the disturbance propagates in a certain amount of time depends on the speed with which it is propagating. Okay. Now, the refractive index of the glass slab, it increases as you go down. Refractive index is inversely proportional to speed. Okay, that means the speed of light is faster in the upper layers of the glass slab and it is slower in the lower layers of the glass slab. Okay, refractive index increases as you go down means speed decreases as you go down. So if you draw the wavelets on the right side, okay, the disturbance, once it enters into the slab, it travels different distances from the sources. Okay, for the first source is close to a region where the refractive index is low, means the speed is high. Speed is high, so the wavelet expands more. Okay, let's take it like this. Yeah, it expands more. But okay, not as much as it expands to the left, that is in light. Okay, it doesn't expand as much as it expands in light. But inside the slab, it expands to a greater distance compared to the distance to which the last wavelet expands. Okay, let me adjust this. We'll change the color a little bit. It's not properly visible. Take it in black itself. Okay, this is what would happen. Okay. In the upper layers of the slab, light travels faster. In the lower layers, it travels slower. Okay. So in the upper layers, the wavelet expands to a greater distance. Lower layers, it expands to a lesser distance. Fine. Effectively, what will happen when light enters into the glass slab? You draw a common tangent to these wavelets. The common tangent will be like this. Okay, you can imagine infinite other wavelets in between. Rishi, did you understand?
Yes, I understood.
Huh. So the beam which was traveling horizontally, okay, and its wavefront was vertical, it now bends like this. The wavefront tilts a little bit, therefore the light also bends. Okay, so immediately after entering into the glass slab, it bends by a small angle. Later, it bends further also, because now you have to imagine secondary wavelets again. Okay, and you will see that it will bend a little further. Okay, I mean, it will keep on bending actually. It won't just bend once and travel straight like this. Fine. So, like, Rishi, are you getting the basic picture, like how to visualize a wave propagating forward or not?
Yes, sir, I'm understand.
Okay. Try to solve some simple questions based on Huygens wave theory. Okay. And this derivation is important. It is there for CBSE also. Okay. And if you can understand this derivation, then then you will be able to answer other questions also based on Huygens wave theory. Okay. So try deriving Snell's law from Huygens wave theory once on your own. Okay. We'll continue in the next class.